Okay, and we are live. So this is the study group session for the University of Austin or University of Texas at Austin with Great Learning study session, March 2nd, 2021. We're going to be doing practice with NLP using the fake and real news data set at the link right here. I'm going to start a new notebook here. So this, the notebook I'm loading up right here is on Kaggle's cloud instead of on Colab. Slightly different interface, slightly different collection of modules that they have available. All of it's still running on Google servers, so it's functionally very similar. Got access to the same toys.
Okay.
So the first step I'm going to do is just load the data into a couple of data frames. Oh, I accidentally did that backwards. Okay, and now that I've loaded it, I'm going to just see how the data's configured. And I'm going to look a little bit closer because I'm noticing there's title, text, subject here. So just going to read a couple of those individually just to see what the length on those typically is. Okay. And then same thing with text. Ah, that's much larger. Interesting. Okay. And then one last thing I want to check. How many distinct objects do we have in subject? And I always forget this one. I want to say it's count distinct, but I know that's SQL. Unique. Nope. Am I misspelling it? Oh, that's why I'm misspelling subject. Okay. And there's only two there. Oh. Well, that's not going to work.
What's up?
So one of the things I was looking at was I wanted to see if I could use subject as a feature in this. And if I check, if I use fake news articles, they have 5 different subjects of that they'll list, whereas for real articles. There's only political news and world news. So not quite as useful there.
Okay.
So I'm going to drop subject, and date I'm also going to drop. So I'm going to, and I think, I'm just going to use title for classification here, because if I go for text, we're going to have some very long articles and it'll take a while for compute time, but a lot of the steps will be similar. So the first thing I'm going to need to do is merge these two, because currently the real articles are in one data frame and the fake articles are in a second. So that's going to be append, but let me see. Real.shape. Okay. Okay. And I apologize, I don't remember the correct. Oh, I guess that was it. Okay, so it's just going to be append. But before I can do that, I first need to add a column to indicate which ones have truthful information and which ones have facetious information, which ones are fake articles. So I'm just going to add a column to each data frame to indicate which it is. Okay. And so and here's a command you may not have seen frequently, but instead of using head or tail, I'm just going to use sample here, and this will select entries at random. And it looks like there's even some that have no text. Interesting. Let me check. Weird, because this one definitely looks blank here.
Where's that?
Right here, it looks like we have blank text, but it's saying that we don't have any missing entries for text. So let me see if I can pull that one up. I may have trouble because there's going to be two indexes that match that, because I haven't reshuffled the indexes yet. Data.text 12502. Okay. Yeah. Shows one of them as being empty. Fascinating. I'll explore that later. So for this, you wanted to explore TF, IDF, and count vectorizers. So let me pull up the documentation on those. So I want to check something as well. So part of SKlearn's package for TF, IDF vectorizer and also for count vectorizer is it does have some built-in text preprocessing, which you can't use that for the project. They expect you to do all the preprocessing yourself before you feed it into the vectorizer object. However, I'm going to skip straight to using the vectorizer object just to make things a little bit simpler and so that we're not spending as much time on the pre-processing for where it can be done. So just going through encoding, decode, strip accents. Oh, actually, let me really quickly just, as we go along, oh, that's why I misspelled it. Actually, right, it's going to be uppercase. Okay. What did I do wrong? Oh. Okay. So and I'm going to feed a few arguments into the count vectorizer module right here so that we can just do this as we go along. For encoding, we don't have to worry about that. Decode, don't have to worry about that. Strip accents, so I'm going to do ASCII 2. Actually, yeah, I'm going to do ASCII 2. Okay. Oh, and that one is, yeah. And then lowercase is already set to true by default, so we don't have to change the words into their lowercase variants. Preprocessor. Huh. Interesting. So there is some other pre-processing stuff I could feed in here, but I won't be. Okay. Tokenizer, I can feed in a custom tokenizer if I want to, which I won't. Stop words. Just to double check something.
Sure.
Okay. Yep. Stop word. So for stop words, I'm going to be, is it one word or underscore? Underscore. So real quick. And I have to reference something else because I do not remember off the top of my head. What the stop words or the easy stop word list is. Okay, NLTK corpus stop words, English. Okay. So here I'm just taking the stop words list from NLTK, or the standard English one. Next, token pattern, I'm going to leave that by default. It will automatically select individual words out. N-gram range. Okay. For this, I'm going to start by leaving this as one by one tuple. So here, n-gram range. Did you get to the part already with n-grams?
No.
Okay, so n-grams are refer to commonly co-occurring words. Essentially, when it's going through the corpus, if you're pulling up monograms, which is what we typically do, you're just pulling up single words and you're creating a vector out of single word occurrences. N-grams work by creating vectors for pairs of 2 words or 3 words or 4, and then that way it's able to store more of how things are co-occurring and also how how things are co-occurring and also actually, yeah, that's really it. It allows you to capture order as well. So instead of just capturing the sentiment of each individual word, it's capturing the sentiment of a collection of words.
Okay.
And so SK for the count vectorizer for n-gram range, you can feed it a tuple, and the tuple has a min value and a max. So if I put n-gram range as equaling 1 and 1, that means it will only select single words for the vector as the minimum and only single words as the maximum. If I were to change this to say 3, it means it would create a vector. It would create vectors with single word occurrences of single words, occurrences of 2 words side by side, and occurrences of 3 words side by side by side. And I'm assuming it's going to generate those based on the most frequent up until the vector hits the maximum size allowed, which in this case is going to be 1,000. For right now, I'm just going to leave this as 1 by 1, and then we'll come back to that in a moment. Interesting. Max DF. This is one I was not expecting. Allows you to set a threshold at which you ignore certain words. So any word that occurs more than a set amount of time, it'll ignore. And then that way, it's a decent way of trying to figure out what the stop words are in a document, or words that are overused to the point of being essentially stop words. Likewise, they also have a min frequency amount, so you can set it so that you won't use any words that have an occurrence rate of less than a certain amount. Max features, that is the next one that I'm going to set, and that's going to refer to the max number of elements that can be can be created for the vector. And then and we got one more person coming in.
Yeah, it should be Will.
Yep. How's it going, Will? Nope, he's still connecting. How's it going, Will?
Hey, how are you?
Doing fantastic.
Wonderful.
So just to catch you up on what we started here,
Okay.
we're using the real and fake news data set on from Kaggle. This is a data set that contains several thousand real news articles and several thousand fake news articles. And the goal is to try and build a classifier to determine which article there, or a classifier that can determine which articles are real versus which articles are fake. So kind of interesting. We started with briefly looking into the data set, taking a few samples out to see what the typical size is of what we're looking at. And then we jumped into creating, setting up the data set for pre-processing. And we're going to be pre-processing it using exclusively count vectorizer and TF IDF vectorizer. And I have all the pre-processing steps already defined inside the count vectorizer. There is more pre-processing that can be done, but to keep things brief, I was just going over these steps. For the class project, they're expecting us to do the pre-processing outside of the count vectorizer, so actually writing our own functions and everything. Before I continue, was there anything for the course that you're having trouble with, or would like more explanation on?
I think the TF-ID vectorizer, I think that was the one I think I understand it in theory, but not exactly what it's kind of doing.
Okay. That one is pretty easy to show.
With.
All right. Well, in that case, I'll be able to show you in just a moment.
Okay.
So I'm setting, just to walk through what I'm doing right here. I say as I'm getting distracted by trying to type things out. So I'm instantiating both the count vectorizer object and the TF IDF vectorizer object. For it, I'm stripping accent characters and reverting everything to its basic ASCII form. I'm using a set of stop words from NLTK to remove those from the corpus. I'm using an n-gram range of just one, so we're only pulling up single word occurrences at a time. Later, we'll experiment with more. And I'm setting the max number of features in the vector to be 1,000. So it will only encode up to 1,000 words, and anything past that is just going to be chucked. Make sense so far?
Yeah, yeah.
Okay. So I'm just going to run that. Okay, didn't throw an error message. I was sure I probably spelled something wrong there. So first, I'm going to and actually I need to, before I do that, I need to reshuffle the I need to fix the index on data. Okay. And what you didn't see, and to explain what I'm doing here, is the real news articles and the fake news articles were separate data sets. So I'm actually going through first and, or I've merged them, but they have matching indexes now. So I need to correct that.
Okay.
Okay. And just to make sure. Good, that matches. And also, So the news articles have a title, and then they also have the text. The text is pretty large, so just to make sure that I'm not spending too much or spending too much compute, I'm just going with the title for right now. It's pretty easy to change things so that later it can be redone with text.
Right.
Okay. So here, oh, that's in compressed form. How do I uncompress that? One moment. Okay. 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 Oop. Ah. Okay. So you can't, it's not very visible here, but when you're looking at this, the vector is each one of these elements here refer to a different word that it's encoding. And it just, each element here in the columns refers to how many times that word occurred in the title. So let me instead.
So wouldn't your words be the column though, I thought?
Yes. The words are the columns.
Okay.
Let me see if I can actually get one that has something in it.
Okay.
What's the problem with this? These are matrices that are not going to have very frequent occurrences. Okay, so you can see right here the 8th column, which we don't know what word that represents, but if you needed to, you could reverse engineer it. I'm trying to see. There's attributes, vocabulary. Okay. Let me see something. I am not sure. Okay, so this is the all of the encodings and what they represent. So for instance, big is column 99.
Okay.
And of course, because this is a dictionary, it's unordered, so it's very So 7 here, for instance, represents the number 20.
Okay.
That probably is not a great thing because if you think about it,
right.
This is going from most occurring to least occurring. So that 20 probably indicates a particular news channel or something. Well, there's no telling if that's going to be more frequent. Anywho, similarly, if we follow a similar process with the TF-IDF vectorizer, and it's going to make sense in just a moment, or maybe more sense. Okay, so I'm going to need to use sampling again. Oh. Okay, and again. Okay, so we can see this here. So as they explained in the class, the vector that comes out, instead of being simply count of how many times a word is encoded, it has a slightly different value assigned to each word. So for instance, for count vectorizer, if the word taco occurs 6 times in a sentence for whatever reason, then whichever column correlated to taco, that column would have a 6 in it. For TF-IDF, if taco happened to be something that occurred very frequently amongst all of the documents in the corpus, you wouldn't get a 6. The value for taco would be lower, so it might be something like, say, 0.3. So then what you'd actually wind up with is something like 0.3 times 6. So that would be 1.8 for the column representing taco. Does that make sense?
Yeah, because that's right. Because the main difference was because the count counted in that one document versus the TF, IDF, or whatever it is, counts across several documents.
Correct.
Okay, I think, okay.
So if we think back for a moment to linear regression, when you have multiple input variables and you're trying to predict an outcome, it's trying to essentially fit a line to the data. So it's trying to do your output, your y is equal to a weight times the feature plus a bias. And so the more features that you have to have more corresponding weights. And if you have a linear model that's trying to fit a line to something that has 1,000 features in it, it's going to take a lot of data and a lot of time for it to be able to work out the optimal weight for each feature. TF-IDF makes it so that is sort of like setting the starting coefficients a little bit closer to the optimal, to the local minima of the function. Does that make sense?
Yeah, so you wouldn't use TF-IDF if you only have one document, correct? I mean, that wouldn't make sense.
Yeah, it wouldn't make sense to. But that being said, it wouldn't make sense to use a count vectorizer for a single document because you're not really, well, it can, but that's a little bit more complicated.
Okay.
So far, does this make sense?
Yeah.
Okay. At this point now, we have 2 sets of data. We have one using TF-IDF, and then one set of data that's using CountVec, which both are makes sense at this point. Now we have to go and fit a model to this. So I'm going to create 2 sets of training data, or training data and test data. So and just so I can make sure that I got this right, that happened after I set the in. Okay, good. Actually, let me make sure of one last thing. TF head starts from 0. Yeah, okay, good. Just wanted to make sure the indexes still line up properly. Okay. X1 is going to be equal to, actually, I don't even need to put in X1. Y is going to be equal to data dot is real. So I want to say that's the column name I came up with. Yes. And then Okay. And then next, I'm going to want to create 2 sets of training and test data. So and let's go with count that first. Okay. And to make things slightly easier to follow, and I'm just going to add all right, let's see if this runs. Yes, it does. Oh, actually, there's one other thing I need to do. Set the random state so that this is actually an apples to apples comparison. Though that being said, I'm not sure if this will give me the same set of indexes for both, because this is going to occur after this has occurred. So let me see something. Okay, yeah, all of them match up. So yeah, these two are using the exact same sets of indexes. So now to build a classifier from SKlearn dot. Actually, I'm gonna just peek over here. Okay, and we're gonna use a support vector machine for this, or SVM. Why? I can't tell you. I have no idea why. It just seems to work better for this particular problem. Okay. Man, it's just hitting 3 keys at once every time. Okay. Oh. Already I'm doing this backwards. Okay. So what I'm doing here, oh, and I did something wrong. Classification. Classification metrics can't handle a mix of multi. Oh. Doy. Okay. All right. Huh, that was pretty good for a first attempt. So just walking through what happened there. Here we implemented a linear SVC, which is a support vector machine. Essentially, a support vector machine works by casting, it works very similar to linear regression, but it casts it into a higher dimensional space and then tries to fit a hyperplane that separates the data points. They tend to be, they tend not to work for most problems, but there are certain subclasses of problems that they work really, really well for. And there's also a lot of the math behind support vector machines has been better implemented in neural networks since. So from a historical standpoint, they're interesting, but they're not necessarily the best. They're an okay model. We didn't go into them in class, but they're very complicated and, in my opinion, extremely niche. So anywho, after building this classifier, we've gotten an accuracy of 92.7%, which, since this is a balanced problem that has about 200,000 real entries and 200,000 false entries, this is a good metric this is a reasonable metric to use. You could still use area under operator receiver characteristic, or you could use F1 score or something if you wanted to be a little bit pretentious, but accuracy is perfectly sufficient for this. So this is using just the plain simple count vectorizer. If instead we change from the count vectorizer to using the TF-IDF vectorizer, let's see what the change in our score is. Okay, took about as long to fit. And if you look here, you're going to see a very trivial change in the actual accuracy right here. So you might be tempted to say that TF-IDF is a superior model for this use case, but keep in mind we're only doing one split. We've only done one split so far. If we want to make things slightly more complicated, more interesting, and I'm going to copy this because it would take way too long for me to print out otherwise. This is a function that I wrote a while ago for using k-fold evaluation techniques. And this one is really just set up so I can quickly do a set number of folds so I can have a reasonably consistent idea of what the performance is. So I'm going to do that and this real quick. Okay, so model. Okay, that's still, sorry, I'm just double checking to make sure everything's still right. Yep, that's still right. Okay, so model is going to be SVM. The X value is going to be count vec this time. Wait, dat, because vec was the vectorizer. Okay. Let me make sure that runs. And while that's running, let me set it up so I can also do the same with the other one. Yep, okay. And then so what I did here was essentially I just ran 6 k-fold a 6-fold evaluation where I was testing on the count vectorizer data and the TF-IDF vectorizer data. And I recorded 4 scores. I recorded the training score for, oh, I did this in a silly way. I'm going to have to redo this. Okay. Okay. So it records 4 scores: the accuracy on training data, the accuracy on testing data, or the average of both of those across the 6 folds. And then it also takes the standard deviation for both the accuracy training and accuracy on test, so that I can see how accurate it is on average, but also how consistently accurate it is across each fold. So the average accuracy here was 94% on training data, and 85% on test data in both occurrences. And from the look of it, that is strange. One moment, that does not sound right. Huh. Wonder if I have something set up wrong. Either that, or that could just be a very good split, or a very optimal split. Yeah, so the average accuracy on test data, so stuff out of sample, is 85%. And the standard deviation between each of those is about 5%. And you'll see again that that name got reset. That the difference between training with TF-IDF and count vectorizer was very tiny in this case. However, we might be able to make that difference just a little bit bigger by doing, I might be able to demonstrate what can make that difference a little bit bigger by doing an additional step. So okay, 20K. And I'm going to rerun this entire thing. So what I just changed was I now redefined both the real data set and the fake data set as just being the first 20,000 entries. And so this way we're now operating with a data set that's 1/10 the previous data set's size. So of course accuracy is going to go down, but that fix it. Oh, doy, index from 1. Okay, run all. Okay, so this time, now it's making me wonder if I'm doing something, if there's some step I'm getting wrong, because this is very accurate right here, and then this is not. That's weird. I gotta have some step wrong. Oh well. Also, this is kind of strange. Typically, you'd see, since you're working with a smaller data set, that the TF-IDF should give an advantage, should give a larger advantage, because it's going to communicate just a little more signal from the data that you have available, but that does not seem to be the case. fact, it looks like it's working very close together. Huh. Probably more to do with the problem set that we're working with than than anything specific to count vectorizer or TF-IDF. So does all this make sense so far?
Yeah.
Okay. Is there anything that you might want further explanation on?
I'm okay.
Okay.
No.
Then
Yeah.
the other thing I'll experiment with real quick, because I mentioned n-grams before, is if we go back to the count vectorizer and the TF-IDF vectorizer, one additional option is using, instead of using monograms where we're only capturing each vector represents a single word, instead we're going to use n-grams where each vector can represent a single word, 2 words, or 3 words. And it's going to select all of those are the ones that have the largest co-occurrence. Again, building a dictionary up to 300 or 1,000 features. Oh, and actually I need to rerun everything because otherwise that's just going to be using it with a small subsample still. And I suspect this might, oh, that actually didn't take too long to run. Fascinating. And if I go through and look at the dictionary from count vectorizer, you'll notice that the majority of the entries are still single element entries. But as I go down, I'll find things like fact box Trump, so 2-word entry here, or Trump Twitter. Every story that has that in it's a funny story. I don't care what your political opinion is. Those two are always funny together. Tax bill, that's always a tragedy. State Department, yeah, it looks like we're getting almost exclusively monograms, but there's a couple. Oh, finally got our trigram, White House says.
So what determines the n-gram?
So in here, I just fed in the argument that the minimum size of an n-gram can be a single word, and the maximum size can be 3 words. And what it's going to do is it's going to iterate through the entire data set, and it's going to select monograms, bigrams, and trigrams based on the most frequent occurrence.
Oh,
so
okay.
For instance, if it comes across the word butterfly, and that word happens to be the 100th most frequently used word, it'll be in the index. If butterfly flies, those 2 words together happen, let's say 800 times inside your corpus, that would be included in this because we've set the max features to 1,000. But if the words together, butterfly and flies, happens to occur only, or happens to only be like the 2,000th most common one, it's not going to occur. So obviously this will prioritize monograms over bigrams and trigrams, but it means that bigrams and trigrams that are extremely frequent are going to be included. And the advantage of using bigrams, trigrams, or even n-grams that are much larger is that you get the signal from co-occurrences. The order has more meaning to it. So words like not, which on their own don't convey much meaning, convey a lot more meaning when paired with something else. So it allows those words to function. Similarly, you'll notice that with a lot of the tokenizers and some stemming methods, contractions like haven't would change to have and t, where the t is meant as a not, essentially, which again doesn't convey much information when it's by itself. So in theory, this can add some useful signal. Realistically, if we want to get the most out of it, we'd probably want to keep it 2 and 3 instead of 1 to 3. But I was just curious how it was going to play out. And as you can see, most of the occurrences are happening in monograms. So the most common ones are monograms, but there are 2-word combinations that are frequent enough to make the list. And if we look down to see what is the difference in model performance, we see a very slight improvement there. And here, no improvement. Now, if instead, just to try experimenting a little bit more, this is my favorite part once you've got all the hyperparameters together and you're just trying to see, throwing different things together to see what happens. So now I'm going to use just trigrams. Where is it? Run after. So now it's going to take a little bit longer to generate. If I look at the dictionary, you're now going to see just 3-word entries. And oh, wow, the accuracy went way down. So now we're at about 58% accuracy here. And in k-fold cross-validation, yeah, there's got to be something there that's not working. There is no way that accuracy should be at 14% unless I've got something screwed up. I'm going to have to troubleshoot that some other time. Perplexing. But yeah, that's not really optimal there. Wonder if I change this instead to 2 to 4. And we'll see the new vocabulary in just a moment. Yep. In fact, it looks like we're getting almost none that are 4-word entries. Accuracy goes up somewhat, but of course, still below what it was before. And here it's still garbage. So some value there. I wouldn't, actually, I'm curious about something. So we're seeing a dip in accuracy if we do it right here. What if instead of using an SVM, we try something different? And I wonder if this is just going to take too long to train, but we'll see. Okay, so now I'm just going to try this again with a random forest classifier. With random forest classifiers, I typically find that there isn't much of a difference between using count vectorizer and TF-IDF, but again, some experimentation may find different results for different cases. And this will take longer to train. The SVM seems to train very quickly on these data sets. In fact, actually, I want to try one other model as well. but I almost never use it, so I'm actually going to have to look up the documentation this time. Okay. All right. Naive Bayes, Gaussian naive Bayes. That's what I want. Okay. Nope. And just to keep this a little simple. That one's a classifier, right? Oh, come on. Okay. That's weird, but okay. That should work, I think. Okay, and as we can see, the random forest is still trying to fit, and that's because it's got quite a large data set to work with here. This is larger than anything we've worked with in class up to this point. The SVM is kind of optimized for handling this particular type of problem, but the random forest classifier is just, there's a lot of compute to throw at the problem. So it'll take a minute. Does anyone have any questions?
Nope.
No, I don't have any questions.
Anything? So is there anything else while that's running? Oh, that's not what I meant to do. I think that probably covers everything then. I'm curious what the score from this is going to be.
I do want to ask something. So I was typing along with you, and at importing, and I'm using Colab, at importing stop words, I get resource stop words not found.
Okay, let me see this real quick, because this one might be that it needs to be downloaded. So just checking, you're using this one, right?
Yes, so it's that second line that's giving Colab problems.
Okay, let me pull this up. Okay, that's quite the error message. That's strange. Let me check something real quick. No, let me. Oh, okay. Yep, never mind. So let me go here and try this. Okay. No, that's not it, I think. Just copying code directly from Stack Overflow like a true engineer. Okay, let's see if that fixes it. So really the issue here is that the English stop words aren't part corpus is not already downloaded in the collab session. So I believe this is going to download the stop words corpus. We'll see. And let me go back to this because it looks like it finished. Oh. Okay. So random forest classifier actually got similar accuracy to the other two and took about 40 times longer to train. So not exactly optimal there. And then naive Bayes model underperformed. While I'm looking at other stuff, I'm just kind of curious if I go back to 1 to 3. Let's do 1 to 2. Okay. Was there any other or anything else that you're having issues with?
Nope, not so far.
Okay. Any questions in general?
No, this one was pretty straightforward.
Okay.
For the most part.
All right. In that case, I'll wind up tidying up this notebook and then posting this along with the recording on GitHub, and I'll share the links with you guys.
Thank you.
Will, have you got my previous links before?
No.
Okay, let me send you the GitHub link now before I forget.
Okay.
Okay, so the link will be in chat.
Okay.
The GitHub page there contains all of the study sessions that I've uploaded content from. And there's the ones that have the folders are the ones that I actually have recordings for. This one will be titled Study Session 3-21. And I'll probably have everything uploaded probably sometime tomorrow morning.
Okay.
because it takes a while for YouTube to compile everything for the longer uploads like this.
Okay. Thank you. I got it.
Okay, and then the notebook will be up there as well, which will probably be more useful since you already got all the questions answered live.
Right.
All righty. And it looks like the random forest classifier finished a little bit below the accuracy of the other two, and naive Bayes was not quite as effective. Well, I think that pretty much answers all the questions for today.
Cool.
So
Yeah.
I guess we'll wrap up then.
Thank you very
sir.
much, Neil.
I appreciate it.
And thank you guys for your time.
No problem.
You have a good evening.
Bye.